Welcome fellow learners. In the previous video, we explored how state works in LangGraph and where different state schemas can be applied. In this video, we will dive into another crucial concept, reducer functions. Reducers play a key role in determining how updates from nodes are applied to the state. Each key in the state has its own independent reducer function. If no reducer is defined, any new update simply overwrites the existing value. So as shown in the diagram, on the left, we have a version without a reducer, where the state gets overwritten each time. And on the right, with a reducer applied, such as an add reducer, the incoming messages are accumulated or appended in state. So in a sense, reducer function determines how state in LangGraph will be updated. And usually there are two kinds of reducer functions in LangGraph. The first one is predefined reducer functions, like add message from LangGraph or add from the Python operator library. There are second type of reducer functions which are custom reducers, which you can define yourself to handle specific logic. Now let's jump into the implementation and see how we can use reducer functions effectively in LangGraph. So now let's start with the default case when we are not using any reducer function in the state. So in our state schema, we are going to use typedict. So for that part, let's first import typedict. Let's run this cell and it will import typedict. Now over here you can see I have defined the state, and in the state I have defined two keys, name and topics. So name is a string and topics is a list of string. So let's run this cell and it will define our state. Now let's define a graph. So in this graph we are going to first define two nodes. These are two nodes, node A and node B. And let's run this cell and let's import few modules like state graph to initialize the graph, start and end are the two nodes which we are going to utilize in our graph, and this display and image would be used to display the graph in this notebook. So let's run this cell, and now over here you can see the graph. So firstly I have initialized the graph with the help of state graph, and I have passed this typed state, the state which we have defined over here, and then I have added two nodes, node A and node B. These are the two nodes, and then there is a edge between start and node A, and then there is an edge between node A and node B, and then finally node B has a edge from it to end, and that's it. That's our graph. Now let's build this graph and compile this. Let's run this cell and you can see the graph. So over here you can see there is start node which connects to node A, then node A connects to node B, and node B connects to node end. So let's see what does this node A and node B have. So node A receives the state as it directly joins with the start node. It will get the input whatever user will be providing. So this will get the state and it is modifying that state. It is modifying both the keys, name and topics both. So for the name, it is adding learner, this is string, to this name string, and for the topics, it is providing LangGraph in a list as a topics. Now in the node B, it is just modifying one particular key from the state, that is topics. So instead of LangGraph, over here you can see it is passing LangChain to this state. So let's invoke this graph and let's see what will happen. So over here you can see I have provided data input, like for the name I have passed AI, and for the topics I have passed an empty list. So let's run this cell. Now you can see node A receives the input which user has provided, which we have provided, that is name as AI and topics as an empty list. Now node B you can see has received the state which has been changed from node A, as there is an edge between node A to node B. So there has been modification done in the node A which will be transferred to the node B. So state will be changed. So you can see that AI is being appended with that learner. As you can see, this string is added with a learner string. So that's why it is AI learner over here. And for the topics part, it was empty at the start, but with the node A, that topics part, topics list has been changed to LangGraph. Now, when node B does some modification, as we have seen over here, like node B only changes the topics part, you can see that topic part has been overwritten. So instead of LangGraph, in the final output, we do have only LangChain, as node B changes the topics list into LangChain only. So you can notice one more thing also over here, that you need not to update all the keys in the state. it will already be taken care by LangGraph. And another thing is, like, as we haven't used any reducer function over here, that's why it is just overwriting the state which it has earlier in the graph. So this is one of the example where you can see when we do not use any reducer function, what is the default behavior of the state in the LangGraph. Now let's assume our graph has branching. So like there is start node, and a start node has two branches, node A and node B. Instead of this sequential graph, it has a branching state. So let's see how we can create that graph. So over here you can see I've created a graph, so which has two nodes, node A and node B, similar to the previous graph. But instead of having edges between node A to node B, we do have edges, two edges from the start. Like start has an edge between start has an edge from start to node A and start to node B, and then node A also has an edge between node A to end and node B to end. So let's run this cell and let's see how does this create our graph. So over here you can see that this graph has a branching state. Now what will happen when we run the same input to this? So like we invoke this graph with the same input. So let's run this cell, and over here you can see that we have encountered an error, and the error is invalid update error at key topics can receive only one value per step. So you can see when our graph comes to this step, at the end step, it is receiving update from both node A and node B. So you can see in our nodes A and B, node A also updates topics and node B also updates topic. Now when it passes to end node, it receives updates from both node A and node B. That's why it is giving us ambiguous result, and that's why it is causing the error. And we are seeing this error like it can only receive one value per step. So it is suggesting us use an annotated key to handle multiple values. Now here comes the reducer function. So next let's see how reducer functions can help in this case. Now to solve this problem, let's first use some predefined reducer functions. So to define a reducer function, we need to have two things. The first one is annotated class, and second one is the reducer function. So now what is this annotated class, and what will be the use of this annotated class? So this annotated class will help us to add some metadata to these keys wherever we are going to add the reducer function. And this metadata will be used by the LangGraph at the runtime, and it will make sure that what type of update needs to be done for that particular key at the runtime. So LangGraph will take care of the update with the help of this annotated class, which will be having the metadata for that particular key. So as you can see over here, in this case, we have defined this topics key and provided this annotated class with the type of this particular key, that list, this is the list of strings, and the reducer function that needs to be applied at the time of the update. So let's run these two cells. Firstly, import the annotated and the add from the operator, and let's run this cell. It will define our state. So over here you can see the name is not having any reducer function, but the topics key is having a reducer function, which is a add. So now let's create the same graph which we have created earlier, the graph with the branching. And over here you can see the two nodes, and start with edge with both the nodes, node A and node B, and both node A and node B having the edge with the end. Now compile this graph, and it will create the graph, and let's run the same input. Let's invoke the graph with the same input and see what will happen in this case. Now over here you can see it hasn't given us any error, and it has properly appended that topics list. So at the start we haven't provided anything to this topics list, it was empty, but at the end, in the final output, we got both LangGraph and LangChain from node A and node B, as both node A and node B were changing this particular key. So if we see in the node over here, which we have created at the start of this video, node A and node B, node A is also updating this topics key, and node B is also updating this topics key. When we were not using any reducer function, we have seen that the output is overwritten in this particular topics key. Like we are only getting LangChain in the output. But when we have used this reducer function, this add reducer function, it was able to add both LangGraph and LangChain in the output. So in this way, reducer function can help us uh, in the case of branching to get updated information in the output state. Now we have seen that this works and it has given us the result. Now let's say instead of passing just the empty list, if we pass none value to the topics key, what will happen? Will it be able to provide us result or will it not? So let's run this cell and you can see that we have got the error, that is a type error, can only concatenate list, and we have got none as a input, that is not a list. So now what can be done, how it can be solved? So here comes the custom reducer functions. So in this case we can use custom reducer function. So instead of directly using that add reducer function, this add, we can create our own reducer function and apply that to that annotated class, to that particular string, which is this topics key. So over here you can see I have defined a custom reducer function which is getting two inputs from left and right. As you know, this is the case of branching. It is getting input from both node A and node B when it is coming to that end node, and that is defined over here. The left side, from the left node, if it is none, it will just return the right node, the state from the right node, and if it is right node is none, it will return the state from the left node. And finally, if both nodes are not empty, it will return left plus right, which is the same case which we wanted with that add reducer function. Like instead of overwriting, it will just append to that previous list. So let's run that cell, that custom reducer cell, and it will define our reducer function, that custom reducer function. And now instead of passing that add reducer function to this annotated class for this topics key, we can pass that custom reducer function to it. Now let's run this cell and it will define our reducer state. And let's create the same graph which we have created earlier. This is the same graph with two nodes, node A and node B, and this graph has a branch. So let's run this cell and pass the same input where we are passing topics as none, and let's invoke this graph. So now you can see instead of giving error, it is providing us the result. Now what will happen? It will first provide the input to the start node. The start node has a edge to node A and node B both. So it will provide the information to both nodes. As you can see, that information to both node A and node B is same, which we have provided at the start. And this custom reducer function will work over here. As we are getting none from the start node, it will just combine that with the current node and update the state accordingly. So you can see that the expected result is over here, which we have asked for. Now in the next section, let's look at an example of a reducer function which is widely used with the chat models. So in the modern days, most LLM providers supports a chat model interface that accepts a list of messages as an input. And as you know, in LangChain, the chat models takes a list of messages that can be of different types, like human message, AI message, system message, or tool messages. So like human messages are messages where user provides the query. AI messages are the responses from the model. Tool messages is like whatever we get output from the tools that can be fed into the LLM as an input to the model. And system messages are the system prompt or system instruction that we provide to the LLM. So these message objects enable structured multi-turn interactions between users and the models. Now how we can use these messages in our graph? So what we can do, for the prior conversations history, we can store it as a list of messages in our graph state. To do that, we can create a key in our state which holds a list of messages object. Now to hold and append these list of messages continuously, we can create a reducer function, or we can use a predefined reducer function and annotate that key with that particular reducer function. And the thing is, like, if we don't use any reducer function, the new updates will override the previous list of messages. So that's why if we want to append messages, we can directly use a reducer function, add messages, which is being provided by LangGraph directly. So let's see how we can use this add messages reducer function in our graph. So we can import this add messages from the LangGraph graph state module. And let's also import a few messages from the LangChain, any messages, human message and AI message. So let's run this cell and it will import our modules. Now over here you can see I have created a state. This is the graph state where I have annotated this message key with add messages reducer function, and over here I have provided that it can be list of any type of messages. And these any messages, as I have explained earlier, it can be human message, AI message, tool messages, or system message. So let's run this cell and it will define our state. Now to see how this add messages reducer function work, let's first create input message. So input message over here you can see I have created a list of single message and I have provided a content to this human message class, and then I have added this input message with a AI message response. So over here you can see I have provided a AI message with the content, hello, how can I assist you today? So let's run this cell and you can see that now our state is updated with this add messages. At the start it was only input message that hi, and now with the help of this add messages reducer function, this state has been updated. Now there are two benefits of using this add messages reducer function. We can overwrite and also remove the message as per our need. So how this overwriting works? So these messages like human message and AI message, we can provide ID to it. So we can override these messages based on the ID. So over here you can see I have defined input message list which is having two messages, human message with ID 1, AI message with ID 2. Now after that I have used add messages reducer function where first input is input message and second is I am trying to append this with AI message this. But what I have done, I have provided it with the same ID number 2 which I have used earlier. So now let's run this cell and let's see what will happen. So over here you can see that we have the first message, this human message content hi, but we can see that this second AI message hello has been overwritten by this message, hello, how can I assist you today? So here you can see the output. So in this way we can override these list of messages with the help of add messages reducer function by utilizing the ID. Now similarly, if we want to remove few messages from this list of messages, we can again utilize the ID from these messages. So let's see how it can be done. So over here you can see I have created this list of messages and I have provided ID 1, 2, 3, 4. Now let's run this cell, and after that over here you can see what I have done. If the ID of those messages is either 1 or 2, let's remove that message. So to remove those messages I have used this remove message class of this LangChain core messages. So let's run this cell and let's run this cell to delete those messages. Now you can see we have got the list of the removed messages and you can see the IDs for both. So now when we run that add messages where the input is input message and the second input is deleted message, what it will do, it will remove those messages whose are having ID 1 or 2. So let's run this cell. Now you can see we only have a list with two messages, these two messages human and AI, which are having ID 3 and 4. Over here you can see that ID 3 and 4. Now as this type of reducer function is widely used, as I have told you earlier, this type of reducer function where we can have list of any messages with a reducer function which will add or append the message to this list. LangGraph has provided a class which can directly be imported and it can be utilized as a state, such that we need not to create the state separately. So if you see, this is the message state class. This is being provided by LangGraph. We can directly utilize in our graph and it will work same as we have created this graph state. So if you look into this particular message state, you can see that it is having a messages key which is being annotated with the add messages reducer function. So it will work same as we have seen earlier. So let's see how we can utilize this message state in our graph. So I have created a graph with a single node. The node is assistant, which will return the LLM response. I have just provided a default response from this assistant node. So let's run this cell And let's build this graph. Over here you can see there is a node which I have appended. So over here you can see there is a node, assistant node, that I have added to this particular state graph. Then I have created an edge between start to assistant, and then an edge between assistant and end. So let's run this cell, and you can see this has created this particular graph. From start there is a edge to assistant, and from assistant there is a edge to end. So this is clearly a very simple graph. So let's invoke this graph by passing a simple human message. So what we expect, like this human message will go to start, which will pass this message or state to the assistant, which is tasked as to provide response to human message as an AI message, and finally it will pass that response to end, and it will give the result. So let's run this cell, and over here you can see now that messages key from our state has been appended with that particular AI message which is being provided by this assistant. So first message is that human message which is being given as an input, and second message that is being appended to this particular messages key is AI message. So in this way we can utilize this message state directly whenever we need to create or we need to use a state with a reducer function add messages. So now we have seen that how these reducer functions can be utilized in LangGraph. Let's see some real life examples where reducer functions can be utilized. So the first one is meta search result merger. So let's say we need to combine results from multiple search engines like Google, Mozilla, Safari and others. What we can do, we can get the results from these multiple search engines with the help of multiple nodes, and then use a reducer function to deduplicate those results, rank those search results by relevance or confidence score, and get the final result. Second example could be MapReduce summarization, where let's say we are having a large document. So what we can do, we can split this document into multiple chunks, and we can pass those chunks into individual nodes in the graph and get the summaries of those individual chunks from those individual nodes, and then finally use a reducer function which combines these partial summaries from each of those nodes into a single cohesive summary. The third example could be assembling model outputs. So these days we can see that there are n number of LLMs are there in the market, like OpenAI, Gemini, Grok, Quen and others. So if we are not sure which LLM to use, what we can do, we can create a few nodes which can run these LLMs independently and then get the results from those nodes, and then use a reducer function which compares output, scores them and keeps the best of the consensus responses. And the fourth example could be multi-vendor price aggregation. So let's say we have a use case where we have multiple vendor APIs which returns the price for the same product. So our task is to find out the lowest price for that product, which vendor provides that particular lowest price for that product. So what we can do, we can create a reducer function which merges or averages the result to produce a unified price list or select the lowest price. So in this way we can get the lowest price for that particular product. These are a few examples how we can use these reducer functions in real life examples. There can be n number of other real life examples also. So great, we have seen that how these reducer functions can be implemented in LangGraph and what are the benefits of these reducer functions and where we should apply them. In the next video, let's see how one of these real life examples can be implemented using LangGraph. So great, thanks for making till the end of this video. Goodbye until the next time.